Hi everyone, welcome to section 5. Today we're going to be talking about reinforcement learning. We're going to be specifically focusing on cue learning and temporal difference learning. So let's jump right into it with the very first problem on cue learning. So consider the following grid world. We have the rewards shown on the left and the state names on the right. We're told that for state A, the possible actions are right and down. From state B, the possible actions are left and down. And when we're in G1 or G2, we can only exit. Upon exiting a numbered square, we collect the rewards specified by the number on the square and enter the end of game absorbing state X. We also know that the discount factor gamma is equal to 1. And in this MDP, all actions are deterministic and always succeed. So all that means is that there's no distribution over the likelihood of us getting to the next state. We know that when we apply, for example, the right action from state A, we will always get to state B. There's no probability of us accidentally getting to G1 or some other state. We are given the following episodes. So let's just recall here, what are these episodes? These episodes are essentially samples of behaviors that our agent has taken and the resulting state that our agent has resulted in after taking an action from a particular, taking an action, like in this case down, from a state A, and it also includes the reward that our agent got after this particular action sequence. And so these episodes here outline these possible samples of behavior. And the first question we're faced with is, using temporal difference learning, we want to learn the value function v of s. When running temporal difference learning, all values are initialized to 0. And now we have a question which asks, for which sequences of episodes, if repeated infinitely often, does the value function that we're learning with temporal difference learning converge to the optimal value v star for all states s? Okay. So let's take a look into temporal difference learning. So what I've done here is essentially just copied the two main steps that one takes when they're running temporal difference learning. And the two steps are first to acquire a sample of our system's behavior, and then to update the value. So here, the sample comes from executing a policy, pi, at a particular state s. This results in us getting a reward r. And then we add to that the discounted value of the next state. And then the key thing here is to actually update the value at that state. What we'll do is we'll essentially take this blending, this linear combination of the old value at that state that we had, plus the new value that we get. And this alpha here is going to be this learning rate, which tells us how much are we prioritizing old data that we had encoded inside of our v pi of s, or how much do we want to consider the new information we got from our sample. So that alpha, that learning rate, is going to help us trade those two things off. All right, now the question asks us, does the v that we're learning with temporal difference learning converge to v star s for all states? And we're specifically asked this in the context of these episodes. We're trying to figure out which of these episodes would we have to feed into our temporal difference learning to get vs to converge to v star of s. And remember, what I mean by feeding in episodes is just which samples would we have to give to temporal difference learning. For example, this is a sample, this is a sample. So which of these sequences of samples should we give to temporal difference learning so that our vs converges to v star of s? Well, okay, so if we look here, one thing we should notice is that temporal difference learning learns the value of an executed policy. So note here that there's these pi's everywhere here. What does that mean? It means that we fix some kind of policy or some kind of strategy the agent is taking when they're moving through the state space. And we say, if I'm executing this policy, how would I choose an action? what reward would I end up getting, and how would I update my value function. And so here, let's just write this out. So TD learning learns the value of the executed policy pi. And that's again here because we're getting samples from pi, and we're also updating the value of that policy pi. So if we want V pi s that we're learning with temporal difference learning to converge to V star of s, the optimal values for the optimal policy, then, well, we need to be executing the optimal policy. So we need this pi of s that we're getting our samples from here to actually be the optimal policy in order to converge our values to the optimal values that you'd get, that V star of s here. Okay, so can we figure out what the optimal policy is in this deterministic MDP we've been given? So I copied over here our rewards and our states because we can actually figure out for the simple environment what the optimal policy is by just looking at it. So recall that we have no discounting. So we have gamma equals to 1. And our actions are deterministic. Actions deterministic. So to figure out what the optimal policy is, let's take a look at each of these states. So we have state equals to A, state equals to B, state equals to G1, and state equals to G2, and figure out what should pi star of A tell us to do, and what should pi star of B tell us to do, and pi star of G1, and finally pi star of G2. Well, based on this reward structure, which gives us 0 rewards if we just stay at A and B, and gives us plus 10 if we get to G1 and plus 1 if we get to G2, if I start in A, well, what's the best way that I could get the most reward with no discounting? Well, I should just immediately go downwards to G1 and then stop, because that will help me accumulate that plus 10 reward. So if I'm in state A, the optimum policy will be to move downwards. What about if I'm in state B? Well, if I'm in state B and I choose to go down, I will only get plus 1. But if I choose from state B to go left to A, and then I follow again the optimal policy from A to get to G1, then eventually I will get that plus 10 reward at the end, which again, with no discounting, is going to be the best I could possibly do. So from B, the optimal policy will be to go left. And G1 and G2, since the only actions we can take are exit, then we essentially have to just exit here, even in the optimal policy. So now we know what this pi star is, and we know that if we're executing this pi star, then when we run temporal difference learning, we will have the values that we're learning of the policy converge to the true values of the optimal policy. So now our question is, which of the episodes, so which episodes act according to this pi star? Because if we observe those samples from those episodes, then we know we're going to be able to reconstruct V star of S after running temporal difference learning infinitely often. Okay, so let's go back up to our problem here. What I'm going to do really quickly is I'm just going to write out here what the optimal policy says. So it says left here, down here, and then exit and exit. And now we're trying to figure out which of the sequence of episodes will help us converge to the true V star. Okay, well, let's see. If we look at the first one, so episode 1, we definitely do see that if we're in A, we're taking the down action, which is great. This looks like the optimal policy that we wrote down here. And when we're in G1, we're exiting. So that's good. But if I only saw episode 1, so if I only saw episode 1, episode 1, episode 1, I only saw these two samples infinitely often, what would happen is I wouldn't be able to actually learn anything about states B or G2 because they're not present in my samples here at all. So just considering episode 1 on its own infinitely often isn't going to help, but it's a good start because A is behaving according to the optimal policy here, as is G1. Okay, what about episode 2? In episode 2, we see that from state B, we go down. So immediately this tells me that if I'm running episode 2 or I'm involving episode 2 in my strategy here, well, basically I know that this is going to be taking me down the wrong path. It's not following my optimal policy. So what I can do immediately is realize that essentially adding like the episode 2 samples into my learning will only help me sort of get confused and learn a suboptimal policy and will force the value at B to not converge to V star of B because it's executing an incorrect policy. So what I can do already is I can look at these candidate examples here that we've been given for sequences of episodes and essentially rule out any of those that involve episode 2. So what I'm going to do is I'm going to X out this guy and this one, or maybe what I'm going to do is to cross them out like this so they're not in consideration. Then we have episode 2 here, episode 2 is here, episode 2 is here. All right. However, one thing that is nice about episode 2 is that G2, we do actually take the optimal action at G2 exit. But again, because B is not executing the optimal policy, episode 2 will never help us converge the true value for value B if we're using episode 2 in our learning. All right, what about episode 3? In episode 3, we see that from state A, our system goes right. This is already not according to our optimal policy. In fact, even for B, we go downwards, which is also not very good. And so I'm going to cross out any of these examples here that involve E3. Okay, so the only episode, the only sequence of samples that are left is episode 4. What does episode 4 do? Well, in episode 4, when we're in state B, we take left, which is great. That's according to our optimal policy. And when we're in state A, we'll go down. This is also great. Finally, when we're in state G1, we're going to exit, which is also great. So everything seems pretty good in this one, except we have a similar sort of problem as we did in episode 1, where we're not able to observe samples at every single state. So what that means is that G2 will never be able to converge if we only run E4, E4, E4 infinitely often. It will, however, help us converge to V star B, V star A, and V star G1. So based on this question, if we only cared about having these non-exiting states converge, so if we cared about just having A and B converge to V star, then it's actually fine to run episode 4 because we are seeing the optimal policy executed from states A and B. So I'm going to check mark this and say this is going to help us converge, but only for states A, B, but not for all states. And for all states was kind of part of our problem here. So this is sort of a conditional accept of the sequence of E4, 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 but only in the case where we care about these non-exiting states. So really what the right answer is this other, that really none of these sequences will learn a value function that converges to V star of S for all of the states. So there's ways to use these episodes in a correct sequence. In particular, if you use the sequence E2, E4, 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 and then E4 infinitely often, where you first sample E2 with a learning rate of alpha equals 1, then what you're essentially going to do is you're going to ensure that V pi of G2, because remember G2 looked optimal in episode 2, that V pi of G2 is going to equal V star of G2. And then what you can do is just execute E4 infinitely often to make A, B, and G1 converge. So that's one way of designing sort of an optimal sequence of these episodes that help you converge to V star. But from the given answers here, none of them would truly make all of the states converge. All right, next question. So here we're considering Q learning to learn the Q function for every state and action pair. When running Q learning, all values are initialized to 0, and we're asked for which sequence of episodes, if repeated infinitely often, does the Q function that we're learning converge to the optimal Q function for all state action pairs. So let's remind ourselves really quickly of how Q learning works. So I have both temporal difference learning on the left-hand side and Q learning on the right-hand side. And I've specifically done this because they look really similar, but there's some important differences in what we're learning and how we're learning. So in Q learning, we also get a sample of our system, where our system starts in some state S, it executes an action, and it results in some next action. After taking this sequence of state action and next state, we can recover a reward here. And then we can also add to it the discounted best possible value we could get, given our current estimate of the Q for the next state S prime. And one important thing to notice is in Q learning, this action A can be anything. Unlike in temporal difference learning, remember we were querying a candidate policy pi for an action. So we were kind of restricted to getting behaviors from this particular policy pi that we were trying to learn values for. But in Q learning, you can essentially execute any actions you want. They could even be random, and you can still be learning the Q function. In fact, what we're going to do is then do this similar kind of blending between the old Q value that we had for a particular state and action and this new Q value that we're estimating through our sample. And again, we're going to be learning this through this learning parameter alpha, which again weights how much we care about new data versus old information that's stored in our Q function. So what's important to notice here is that the Q function depends on a state and an action. And if we care about learning Q star, the true Q value for every state and action, we need to see every state and action. Because if we don't see every state and action, then we'll essentially never be able to run this update because our samples will never be giving us any signal for these state and action pairs. So if we return back to our problem here, in order for QSA to converge to Q star SA, for all of the state action pairs, we have to see all of the state action pairs. This is the only way for us to actually update our Q values in that table for every single SA pair. So what we're going to do is when we look at these sequences of episodes here, what we really want to ensure is that we always see every state and action pair. So what I'm going to quickly do is I'm going to write down each of these possible states as well as each of these possible actions that we know we need to explore. So remember, if we're in state A, we can go either right or we can go down. So this is like a little table here I'm going to write. I'm going to say this is a state and this is an action here. Okay, in B, we can go left, or in B, we can go down. And then if we're in G1, we're going to exit. And then if we're in G2, we can only exit. So these are all of the state action pairs that our Q function is trying to encode. And we need to see every single one of these in order to update them and have our Q learning algorithm converge to Q star. So let's figure out which of these episodes include which of these state action pairs. All right, let's zoom out here for a minute. So we see that A going to the right, actually really quickly just erase some of this stuff so it's less cluttered. All right, so A going to the right is right here in episode 3. So I'm going to write here E3 contains A going to the right. Is there any other episode that contains that? No. All right, what about A going down? So A down is in episode 1 and also in episode 4. So let's write that, episode 1 and episode 4. What about B going left? So B going left is in episode 4. That's the only one that contains it. And then B going downwards is in episode 3 and episode 2. So episode 3 and episode 2. What about G1 exit? So G1 exit is going to be in episode 1 and episode 4. So episode 1 and episode 4. And then G2 exit is going to be in episode 2 and episode 3. So episode 2 and episode 3. Now, looking at this table that we've drawn here, we can already see that we need episode 3 in order to see the state action pair A right, because it doesn't occur in any of the other episodes. And we also know that we need the episode 4 because that's the only one that contains B going to the left. So we can already look at these sequences of episodes that were proposed here and eliminate any of those that do not contain E3 or E4. So that means that we can get rid of this one. It only contains E1 and E2. This one, it only contains E4. And this one contains only E4, but not E3. All right. We can also actually eliminate this one too, because it doesn't contain E4. It only contains E3. What about all of these other combinations here? Well, in order to see A going down, we need E1 or E4. So here in this sequence, we have E1 and E4. We have E4 here, and we have E1 here and E4 here. So all is good here. In order to see B going downwards, we need to see E3 or E2. So here we have E3 or E2, E3 or E2, and here we have only E3. That's fine because E3 contains information about B going downwards. And then for G1 exit, we need either E1 or E4. And for G2 exit, we need either E2 or E3. And turns out that these 3 episode sequences here, this one, and this one, all contain sufficient amount of exploration of each state action pair to be able to learn the Q star for every state action pair. Cool. Let's take a look at the next problem. In the next problem, we have a grid world, and we have an agent who is trying to learn the optimal policy. Rewards are only awarded for taking the exit action from one of the shaded states. Taking this action moves the agent to a done state, and the MDP terminates. Assume that gamma equals 1, and our learning rate alpha equals 0.5 for all calculations. All of our equations need to explicitly mention gamma and alpha if necessary. First problem says the agent starts from the top left corner, right here, and we're given the following episodes from runs of the agent through the grid world. Each line is an episode that contains a tuple, which is the state, action, next state, and the reward. The first problem says, fill in the following Q values obtained from direct evaluation from the samples. So let's remind ourselves, what's direct evaluation? Well, all direct evaluation is it fixes a policy pi, and then it has the agent experience several episodes while following this particular policy pi. As the agent collects samples, it's going to keep account of the number of times it visited the states and the total utility gathered from each state. When we compute then the estimated value of the state action, what we're going to do is we're going to divide the total utility acquired by the number of times we visited a state and action pair. I'm just going to quickly write here. So direct evaluation fixes a policy and has the agent experience episodes while following pi. As the agent collects samples, it keeps a count of the number of times it visits states and actions, and the total discounted utility for each state. Then compute estimated value by dividing the total utility by the number of times we visited the state or state action pair. So what does that mean for our problem here? Well, we're trying to use direct evaluation to obtain the Q value of the state 3-2 and taking the action north. How can we do this? Well, we can first look through all of our episodes, and we want to figure out the number of times that we ever saw 3-2 and north. So 3-2 and north shows up here, and then 3-2 and north shows up here in these two episodes. So we already know that we're going to be dividing by 2 because we visited 3-2 north 2 times. Now, what do we need as the numerator when we're computing direct evaluation? Well, we need to figure out what the total utility was from each of these. How are we going to do this? Well, we know that in this sequence of states and actions that the agent took, when it's in 3-2, it's going to get an immediate reward of 0. But then the next state it's going to end up in is going to be 3-3, and it's going to take the exit action and receive plus 50 reward. So if we write this as the total discounted utility it's going to get 0 immediate reward plus 50 times gamma, after which it exits and it terminates. What about in this particular episode? So here it's the same setup. So here we're in 3-2, we get 0 immediate reward, but then we exit and we get plus 50. So we're going to say plus 0 plus 50 times gamma. And as you remember from what the definition of direct evaluation is, we're going to divide this total utility by the number of times we saw this state action pair. So here we saw it twice, so we're going to divide by 2. Now, one nice thing in this problem is that gamma equals 1. So this makes our calculation super easy. It's just 50 plus 50 divided by 2. So it gives us a total Q here from direct evaluation as 50. What about Q of 3-2, S? So first thing we're going to do is we're going to figure out how many times did we actually see 3-2, S. So 32, S doesn't appear in episode 1, doesn't appear in episode 2, does appear in episode 3 right here. And 32, S does appear also here in episode 5. We're going to follow the same procedure as we did before. Let's figure out what the numerator is. We already know that we're going to have 2 in the denominator. The numerator is going to have the total discounted utility from episode 3 and episode 5 added together. So here, if we started in 3.2, we got an immediate reward of 0 plus 30 times gamma when we exit. And then in the second scenario, it's the same deal. We have immediate reward of 0 plus 30 times gamma when we exit again. Turns out another easy calculation, 30 plus 30 divided by 2, it's just 30. All right, what about the final scenario here? So the final scenario, we're trying to compute the Q value of 22, E. This appears in episode 1, in episode 3, 4, and 5. All right, let's write down what our direct evaluation is going to divide by. It's going to divide by 4 because we saw this sample 4 times. And then our numerator, we're going to compute 1 by 1. So here, our immediate reward is 0. Then we're going to take another step and get another 0 reward discounted by gamma. Then we're going to take one more step in our policy, and we're going to get 50 times gamma squared. That's what we get as the total utility in episode 1 when we start from 2.2. What about in episode 3? So in episode 3, we have 0 as our current reward. Then we take a step, we get 0 times gamma, and then we take another step and we get 30 times gamma squared. Episode 4, we're going to have 0 plus 50 gamma squared. Sorry, technically this is 0 gamma here. And then the last scenario is going to be 0 plus 0 gamma plus 30 gamma squared, all divided by 4. Again, turns out we're in a really nice scenario here. All of our gammas are equal to 1. And so this ends up just being 50 plus 30 plus 50 plus 30 divided by 4, which equals 40. All right. Q-learning is an online algorithm to learn optimal Q values in an MDP with unknown rewards and a transition function. We're given here the update equation in its full form, where typically this component here is written as sample in a lot of the lecture notes. But this is just the full update for the Q-learning algorithm. We're reminded that gamma is the discount factor, alpha is the learning rate, and we get a sequence of observations that are these states and action pairs. Given the episodes that we've seen here in part A, we want to fill in the time at which the following Q values first become non-zero. Let's pause for a second. Why would they be equal to 0? It's because Q values are always initialized to 0 at the very beginning before we've gotten any evidence from our samples. And then we're going to make them non-zero through this update by observing some sequence of observations of these state action pairs. So we're trying to figure out the first time when the Q value becomes non-zero. That means we've actually done some non-trivial update to our Q function after observing some relevant information. When updating the Q values, we should only go through each transition once, and in the order in which you're going through them should be the transition in episode 1, the transitions in episode 2, and so on. So all that means is that we're going to start in episode 1, and then we're going to first observe this sample, then this sample, then this sample, and so on. Then we move to episode 2, and we go down the list. Our answer should be in the form of episode number and iteration number, where iteration number is the Q-learning update iteration in that episode. What that means is that if we discovered that this sample helped to make one of these Q functions non-zero, then this would be episode 1 and iteration 3, because it took us 1 iteration, 2 iteration, 3 iterations of Q learning in episode 1 to actually make a non-zero entry. And we finally are told that if the specified Q value never becomes non-zero, then we write never. So what I did was I copied over this table and the Q functions that we're interested in here on the next page, just so we have a little bit more space to write. I also copied over the Q learning update rule, which will help us actually go through the machinery of applying Q updates. So because we're updating this in order to figure out what Q of 1, 2 east is, so for example, this is the first time right here in episode 1, iteration 2, when Q12 is ever even attempted to be updated, what we actually have to do is update all of the entries before. So in order to figure out what Q12 east is, I need to first do an update on Q13 south. And I'm going to keep having to do this for all these episodes because we sort of traverse this way through all of the data. And the data kind of depends on each other because, as you can tell here, through this max over the Q value of the next state, we can tell that if I'm updating the Q value at some particular ST for some action AT, depending on what the Q values are of the next state, QST plus 1, I'm going to get a different Q value here. So this interdependence means that we have to actually be updating all of these values in the sequence that we're seeing them in order to get the values at other states that depend on the next values. So let's see this in action, because that's, I think, the clearest way to understand it. And to do this, let's consider episode 1. What's the first thing we're going to update? Well, we're going to have to update Q of 13 in south. This is going to equal 1 minus alpha times our old Q value of 13 south plus alpha times the reward of being in 13, taking the action south, and ending up in 12, plus gamma times max over the actions that we could take, where we're now looking at the Q value of the next state. So now we're going to plug in 1, 2 in here, and we're going to try to figure out what's the best Q value we could get at the next state after maximizing over all the actions. Now, we know a bunch of information about our problem, so let's plug some things in here. We know that according to our problem, alpha equals 0.5. We also know that gamma equals 1. So this means that here, this is always going to equal to 1. What else do we know? Well, we know what the reward of being in state 13, taking the south action and ending up in 12 is, because that's what our sample here tells us. It tells us we're going to get 0 reward. Finally, because Q learning initializes all of the Q values to be equal to 0 at the very, very beginning of the algorithm, since we haven't actually updated anything, we know that the old Q value of 13 and action S is going to equal 0 because we haven't actually updated it. So nothing is actually happening to that value here, and it's contributing nothing to our update. So when we plug all this stuff in, what we're going to see is we're going to have 0 here plus 0.5 times 0 plus max over A prime of Q of 12 and A prime. All right, so that's gotten a lot more simple. Now let's think about what this max over the actions of the Q value at the next state could possibly be. Remember, we're at the very first step of our Q learning algorithm. So what this component of Q learning is trying to do is it's trying to look at the Q values that we have so far, and we're trying to query that at the next state we could get to, 1, 2. And we're trying to figure out which action would result in the best Q value at the next state, 1, 2. Unfortunately, we haven't updated anything yet. And so the entry for Q12 and any action is going to equal to 0 for all A prime in our action set, because we haven't updated it yet. So it turns out this max over all actions is always going to equal to 0 no matter what action you plug in. And so in a little bit anticlimactic fashion, this Q function actually doesn't get updated at all for 1, 3, and south, because so far we haven't seen enough information about anything to actually propagate some non-zero values throughout. All right, let's do the next update. So let's do Q of 1, 2, east. I'm gonna start writing sort of a little bit more quickly, because now we know what a lot of these entries are, and they're always kind of fixed. So we know that it's always gonna be 0.5 times Q of 1, 2, east that we had before, plus 0.5 times, what's the reward that we get at this particular sample? We get 0, plus max over A prime of Q of the next state, which is 2, 2, A prime. What do we know? Well, again, something anticlimactic. We haven't ever updated a 1, 2 east, so this is going to be 0. And we haven't actually updated anything about the state 2, 2 for any of the actions. So this is also going to be equal to 0. So nothing interesting happens here. In fact, what we're going to notice is that for all of these samples here, nothing interesting is going to happen in terms of the Q value update. And that's because they always have 0 intermediate reward. We haven't updated any relevant Q functions yet. And it's only until we see this final sample here at 3, 3, when we take the action exit, do we see a non-zero immediate reward that's going to eventually propagate through the other relevant states that depend on it. So what I'm going to do is I'm just going to quickly write here that Q of 2, 2 east will also be 0 in episode 1, and Q 3, 2 north. This one I'm actually going to write out really quickly because it's an interesting example to see how information sort of propagates through the Q learning algorithm. So it's going to still be equal to 0, but let's actually look at the structure and think about why it's going to be kind of interesting. So Q3, 2 north is going to be equal to 0.5 times Q of 3, 2 north plus 0.5 times an immediate reward of 0 plus max over A prime of the Q values of the next state, which after taking the north action from 3, 2, we get to 3, 3. And we're evaluating the Q function for all these different candidate A primes. Okay, so we haven't actually updated anything about Q3, 2 in the past. Its Q value is still 0. But here's where it gets kind of interesting. So right now, when I take this max over the Q value at 3, 3, this is still equal to 0 for all actions. And that's because I still haven't updated the Q value for the state 3, 3 for any action. But notice the next sample we're going to see here is actually going to be updating the Q value at state 3, 3 with some non-zero interesting value. So what that means is that eventually when we return back to updating Q of 3, 2, which relies on Q of 3, 3, eventually when Q of 3, 3 gets updated to some non-zero number, it's going to propagate that value here to Q of 3, 2. And that's how you're going to start seeing these terminal values that we're seeing here. So this plus 50, this minus 100, plus 30, plus 50, plus 30, eventually work their way back through the other states that depend on the values here at the exit states. But it's going to take a few iterations to have those numbers actually propagate. So let's actually write out, I'm going to erase all this stuff here. So let's actually write out that this will still equal 0, but let's now write out Q of 3, 3 exit. So it's going to be 0.5 times Q of 3, 3 exit. This guy still 0 because we've never updated the state 3, 3 with the action exit. But now our immediate reward is plus 50. So now I'm going to put 50 here where we write down our reward. And now we're saying max over all next actions for Q of the done state A prime. In the done state, nothing interesting really happens. So this guy will always equal to 0 because the MDP terminates. But something interesting has happened, because now here we're going to get 50 times 0.5. And so this is the first time that state Q33 exit becomes non-zero. So here we now have a final Q value of 50 over 2, which equals 25. So this has happened, this event here happened in episode 1 and in iteration 1, 2, 3, 4, 5 of Q learning. But this is for one specific state. So in episode 1, iteration 5 is the first time that the Q value of state 3.3 and the action exit becomes non-zero. Unfortunately, we haven't actually seen non-zero entries for any of these candidate states that we're interested in solving for this problem. What that means is we have to keep moving forward with the next episode to update the Q values and see what happens. So now we're going to be going to episode 2. Essentially, what I can tell you right now is that nothing interesting is going to happen until, once again, we get here to updating the Q value of state 2.1 when you take exit. So as shorthand, I'm just going to really quickly here write that Q of 1.3 south is going to equal 0, and feel free to work these out on your own. Q of 1.2 east is going to equal 0, and Q of 2.2 south will also equal 0. The interesting one is going to be Q of 2.1 exit, which will equal 0.5 times Q value of 2.1 exit. That's our old Q value, plus 0.5 times the immediate reward we're getting, which is a minus 100, plus max over all next actions after we get to the done state. All right, so Q of 2.1 exit, we've never updated before, so this equals 0. And when we're in the done state, we can never do better than getting a value of 0. Doesn't matter though, we're still getting some interesting non-zero value here because we're seeing here 0.5 times minus 100. And so again, we're actually seeing an interesting non-zero update for the Q value at state 2.1 after taking the action exit. And so this is going to be minus 50 here. And this occurred in episode 2, iteration 1, 2, 3, 4. All right, so in episode 3, we're going to see a very similar structure. Essentially, all of these Q values are going to equal to 0 until we actually update the Q value at 3.1. So essentially, I'm just going to write Q of 1.3 north, sorry, 1.3 south equals 0, Q of 1.2 east equals 0, Q of 2.2 east equals 0, and Q of 3.2 south equals 0. Now we're at Q of 3.1 exit. And this one, if we actually worked through the numbers here, we would end up getting that we're going to get an updated Q value of 30 over 2, which will be 15. All right, and this happens in episode 3, iteration 5. All right, we're almost getting to the interesting parts, I promise. Let's just go through episode 4 here. So in episode 4, nothing much interesting is going to happen until we get actually to this state. So I'm just going to quickly write down here that Q of 1, 3 south equals 0, Q of 1, 2 east equals 0, and Q of 2, 2 east equals 0. But now let's update Q of 3, 2 north. So Q of 3, 2 north. So it's going to be 0.5 times our old Q of 3, 2 north plus 0.5 times, what's our immediate reward here? Just 0. That's not too interesting. But now we're going to be doing plus max over all next actions of Q of 3, 3, because 3, 3 is the next state we get to. And all possible actions we could take from 3, 3. Why is this interesting? Well, Q of 3, 2 north itself, like this value here, hasn't changed. So this isn't the interesting part. What is interesting is this max over the best Q that we could get at the next state 3, 3. Notice that we updated here Q of 3, 3 for the action exit. So far, if I plugged in any action here, except for exit, I would always get 0. But if I plug in the action A prime equals exit, then I get a Q at this state, which equals to 25. If A prime equals anything else, then I get Q equals to 0. So if I'm trying to maximize the Q value here, I'm going to choose to exit, and I'm going to acquire 25 as my Q value. And so this means that here we're going to get 0.5 times 25 as our updated Q value for the state 3, 2 when we're taking the action north. This happens in episode 4, iteration number 4. Awesome. We're going to update also here Q of 3, 3 exit. That's going to get updated again because we have another sample of taking the exit action from 3, 3. And it's going to get updated to some non-zero number. So I'm just going to not write this out because we only care about seeing when these values actually become non-zero for this particular problem. But eventually you can get some non-zero number here, which I believe should be 25 over 2 plus 30 over 2. Final episode, episode 5. In episode 5, many of these values won't change, but something interesting is going to start to happen when we start updating Q of 2, 2 east. So I'm going to just quickly write down here that Q of 1, 3 south is not going to change, and Q of 1, 2 east is not going to change. But Q of 2, 2 east, which is this sample right here, is actually going to start changing. So let's write down 0.5 times our old Q value at 2, 2 east, plus 0.5 times our immediate reward is just 0, plus max over the Q value at the next state, which the next state here is going to be 3, 2. So 3, 2, A prime. Well, so far, we've never updated Q22 east to be anything interesting, so it's just going to be equal to 0. But have we ever updated the Q value at 32 to be something interesting? We actually have, right here. In episode 4, we said that Q of 32 when you take the north action is equal to 25/2. So we know that this is going to equal, so if I'm choosing A prime to equal north, then I'm going to get a Q of 25/2. If I take any other action, so far that Q value is going to be equal to 0. So if I'm trying to maximize my Q value, what am I going to choose? I'm going to choose to take the action north. I'm going to acquire 25/2 as my reward. And this means that what the Q value is going to be here at state 2,2 with the action east is going to be 0.5 times 25/2. And we have seen the first time when the state 2,2 and the action east becomes non-zero. When does this happen? It happens in episode 5 in iteration 1, 2, 3. What about the next state here in our list? So we have 3, 2, and south. So we want to update Q of 3, 2, south. 0.5 times our old Q of 3, 2, south, plus 0.5 times our immediate reward, just still 0, plus max over A prime of Q of 3. What's the next state we get to? 3, 1 here. So the next state we get to is 3, 1, A prime. All right, so have we ever seen an interesting non-zero value for Q of 3, 2 south? No, not really. So this is just 0. What about some interesting value for 3, 1? And we have. So here, when we were updating Q of 3, 1 for the action exit, we saw that we accumulated a non-zero value here of 15. So here, if A prime equals exit, then we get Q equals to 15. If A prime is anything else, then Q is equal to 0. So to maximize, what are we going to do? Well, we're going to take the action exit here. And so this is going to give us a final non-zero Q value of 15/2. So this is going to be episode 5, iteration 1, 2, 3, 4. Finally, we'll also update the Q value of 3, 1 exit. But what I want to do right now is just sort of pause and see, okay, we finished applying Q learning for each of these episodes and for each of the iterations of that within each episode. Now let's figure out if we're actually able to answer our original question, which was at what episodes and which iterations do we actually update the Q values for 1, 2 east, 2, 2 east, and 3, 2 south to be some non-zero number? Well, if we look at what I've highlighted here, Q of 3, 2 south, we updated for the very first time right here. So we did this in episode 5, iteration number 4. What about for Q of 2, 2 east? When was the first time we ever updated that? That was right here. And we did that in episode 5, iteration 3. What about the Q value of 1, 2 east? Did we ever update this? Well, so it turns out here we didn't actually. Just doing one pass through all these episodes was not enough for us to actually update the Q value of 1, 2 east to be something non-zero. So here, would write never. And with that, we've completed this particular problem, and we know the episode numbers as well as the iteration numbers that these Q values for these particular states and actions became non-zero for the very first time. All right, let's take a look now at the final part of this problem, part C. So this part of the problem is asking us to look at actually a different window of samples than we usually look at to update our Q values in Q learning. So typically we look at this window of a current state, an action we took at that state, the next state we get to, and the reward we got. And instead, now what it's saying is think of using an update rule which uses a larger window to update these values. So this larger window is going to look at a state, action, reward, and next state. But it's going to say, ooh, what about the next state, or the next action you could take, the next reward, and the 2 states after that you could reach. So you're going to get a sample essentially that shows you Pac-Man taking an action and then taking another action. Versus in typical Q learning, we would just see this window of actions and states. And we want to give an update rule for QSA given this larger window. So how we're going to go about this? Well, the first thing I would do is write down just the standard Q learning update when we just have this intermediate window right here, because that window here still exists right here. These two are the same. So what I'm going to do is I'm going to write down 1 minus alpha Q of STAT plus alpha RT plus gamma max over A prime Q of ST plus 1 A prime. But now how can we use this extra information right here? This extra action, extra reward, and extra next state. So what we can do is look actually right here. This max over the Q value at the next state is actually something right here that we have a little bit more information about, because we actually are told what the next action is, as well as what that next reward will be, and the state 2 steps from now will actually be. So we can actually sort of do this nested Q learning update by expanding this out. And what I'm going to do is I'm going to rewrite here 1 minus alpha times Q of STAT plus alpha times RT plus gamma. But now what we're going to do is we're going to just essentially do another Q learning update in here. So we're now going to do another 1 minus alpha times the Q function of ST plus 1, AT plus 1, plus alpha times the reward at time t plus 1, plus gamma of the max over A prime of the Q of ST plus A prime. Just going to move this over here. Long equation, but it's essentially this nested Q learning update where all the information that we have is this state, the action we took, and the next reward we got. So I'm just going to annotate this like this. So we're given all of this information, which we plug in from the very first sort of window of observations. And then we're also given a little bit more information because our window is larger. So we're going to plug in the action, the reward, and the next state into this bi-level, this nested Q learning update that lets us incorporate this larger sequence of observations. Cool. All right, let's look at the final problem in our worksheet. So in the final problem in our worksheet, we're faced with this issue where when we're using Q learning for some of our problems, the size of the state space might be too large for a grid to hold in memory. Because remember, when we update Q values, you can think of them as being this large table where for every state and for every action, you have a little grid cell and you're holding what the Q value is in that particular grid cell. But if your state space and your action space are really big, it's going to be really hard to hold this in memory. So to solve this, we're going to switch to a feature-based representation of Pac-Man state. We have two features here, FG and FP, which are defined as follows. FG and FP both take as input state and actions, and they just essentially consider different features to evaluate for FG or FP. So here FG considers the number of ghosts within one step of state S, number of ghosts Pac-Man touches after taking an action A from state S, and the number of ghosts within one step of the state Pac-Man ends up in. FP considers the number of food pellets within one step of the state S, and the number of food pellets eaten after taking action A from state S. For this Pac-Man board, the ghost will always be stationary, and the action space is left, right, up, down, and stay. What we now want to do is calculate the features for the actions left, right, up, and stay. So all this means is we're going to plug in left, right, up, and stay into these equations here and see what they evaluate to. So I'm going to abbreviate this as L, R, up, and ST. And let's get to it. So we're trying to compute FG, which is the first feature function here, for a state S, and we want for the action, let's say, left. So this is going to be A of S plus B of SL plus C of SL. Okay, what is A of S? A of S is the number of ghosts within one step of state S. So in state S, if Pac-Man is right here, within one step of this state, there's 1, 2 ghosts. So A will equal 2. What about B of S? So B of S here is the number of ghosts Pac-Man touches after taking action A from state S. So if Pac-Man is right here and he goes left, then he's going to touch 1 ghost. What about C? The number of ghosts within one step of the state Pac-Man ends up in after taking action A. Well, if he takes one step here, there is a ghost right here within one step of the state that Pac-Man ends up in. So this feature, so f of g, the feature function f of g, for the state S when Pac-Man takes the action L is going to evaluate to 4. What about f, g, s, r? Well, if Pac-Man goes to the right, there's going to be 2 ghosts within one step, then there's going to be 1 ghost that Pac-Man touches, and 1 ghost within one step of Pac-Man's next state. So it's going to be 4 again. FG of S up. If Pac-Man is in state S, there's going to be still 2 ghosts within one step because he's surrounded by ghosts on left and right. But after he goes upwards, there's going to be 0 ghosts that he touches and 0 ghosts within one step. So that's going to be 2. Finally, FG of ST, or stopping, is going to evaluate to 2 ghosts still, because he's surrounded from the left and right. But if he chooses to stay, there's going to be no ghosts he's touching, but there's actually going to be 2 ghosts within one step of him. So 4 here. What about the other feature functions? So we have F here of P, S of L. So this is going to be D of S plus 2 times E of S, and our action is left. What's this going to be? Well, this is going to be the number of food pellets within one step of state S. So if Pac-Man is here in the middle, there is 1 food pellet within one step of this state. So we have 1 plus 2 times, and this is the number of food pellets eaten after taking the action A from state S. So if Pac-Man is here in the center and decides to go left, he won't have eaten any pellets, so the total feature count here is just 1. FP of state S and action R is going to look really similar. It's just going to be 1 plus 2 times 0 equals 1. FP of the state S and action up is going to be more interesting, because now when Pac-Man moves upwards, there's going to be a food pellet that's within one step, but he's going to also eat a pellet after that one action. So we're going to get 2 times 1 here, which is going to be a total of 3. And finally, FP of state S and the action stay is going to be 1 plus 2 times 0, just 1. All right, next question. After a few episodes of Q learning, the weights are WG and WP. Calculate the Q value for each action, left, right, up, and stay. So one thing we should remind ourselves is, how does the Q function representation look like when we're using these feature values? And so the key thing here is that now our Q function is no longer going to be a table that we're keeping in memory. It's now going to be represented as this linear combination of features. So in this case, we have 2 features. We have FG, SA, and this linear combination is going to be parametrized by these weights. So we have a weight, WG, which essentially captures how much of the feature FG at a particular state S and an action A is coming into play for the Q value for that particular SA. And then we're going to add to it the other feature, FP, at state S and action A, and it's also weighted by its own respective weight, WP. The key thing is that when we're doing this Q representation, that is this linear combination of features, we're not sure beforehand what these weights are. So we're given these feature functions here. You can see them defined right here, but we're not exactly sure how to choose WG and WP to accurately represent the Q value at any given S and A pair. So what Q learning is going to be doing is updating the value of these weights, WG and WP, based on observing some kind of observations of the agent. And so let's take a look now at this part B here. We've been told that we've been running Q learning, and after several of these episodes, we have discovered that WG so far seems to be -10 and WP seems to be 100. Now we want to calculate the Q value for each action from the current state shown in the figure. So all that means is that we want to basically just evaluate this equation, which represents our Q function, our approximate Q function. So let's try to do that. So if we're evaluating the Q function at state S with the action L, then we're going to put here WG times FG of SL plus WP times FP SL. We have been told that these two numbers, WG equals -10, WP equals 100, and we've already computed all of these F's here for FG and FP for each of the state action pairs. So we know that FG of SL is going to be equal to 4, and FP of SL is going to be 1. So equals 1, and this equals 4. So what's going to be the total approximate Q with our current weight estimates at this state in action? It's going to be -10 times 4 plus 100 times 1, which equals 60. We can do the same thing for Q of SR. It's going to be -10 times 4 plus 100 times 1, so it equals 60 again. Q of S up equals -10 times 2 this time, plus 100 times 3, and that's going to equal 280. It's looking really good to go upwards from this current state that Pac-Man's at. And finally, Q of S state is going to equal -10 times 4 plus 100 times 1, which equals 60 as well. All right, we observe a transition that starts from the state above, so Pac-Man being right here, it takes the action upwards, ends up in state S prime, and it receives the reward of 250. The available actions from state S prime are going to be to stay there or to choose to go downwards. If we assume a discount of 0.5, we want to calculate the new estimate of the Q value based on this episode. So how are we going to do this? Well, what we want to do is write out our Q function here. So we're going to say that Q of SA, and in this case, what is our action? Well, we already took this action up. So it's going to be SU is going to be equal to the reward that we got, so 250. Let me actually write this out here. So we have R of S, our action is up, and our S prime is going to be that next up state, plus gamma times max A prime of Q of our S prime, A prime. So we know a bunch of these components. We know that R of SU S prime is 250. We are told that we have a discount factor of 0.5. And now we're essentially just trying to figure out what's the max overall actions of the Q value at the next state. Well, we're told that at the next state, the only available actions are down and stay. So we know that it's going to be 250 plus 0.5 times the max between Q of S prime down and Q of S prime stay. Well, now that we've seen this, let's figure out what these Q values actually are. And in order to figure these out, what we're going to do is we're going to query this featureized representation of our Q function. So here we know that Q of S prime D equals WG times FG of S prime down plus WP F of S prime down. And this is going to be the same here, except with the stay action. So we have Q of S prime stay equals WG FG S prime stay plus WP FP of S prime stay. We have all of these values already. We've computed most of them here. We know what our weights are from the prior part of the problem. That's still minus 10 and 100. And so it turns out if you actually write all these out, this Q function actually equals 0, and this Q function also equals 0. So not the most, sorry, no, that's incorrect. This Q function equals 0 on the right-hand side, but this one actually does not. This one equals minus 20, actually. The key thing is we're trying to maximize between these two. So if Pac-Man decides to go downwards from state S prime, he will get a Q value of minus 20. But if he chooses to stay, he'll get a Q value of 0. So if he's trying to choose between the action that maximizes the Q value, it's better for him to stay because it gives him 0 Q value than to go downwards because it's going to give him minus 20. And so this will ultimately result in 250 plus 0.5 times 0, which will end up in the new estimate of Q value for state S action U to be equal to 250. Okay, final question. With the new estimate and learning rate alpha of 0.5, we want to update the weights for each feature. So remember before I said that when we have this approximate representation of our Q function that uses these weights that trade off how much each feature contributes to the representation of Q, we are trying to actually learn these weights because we're given the features and we just don't know how much FG and FP contribute to the approximate value of Q. So what we want to do now is actually do an update on WG and WP. given this new estimate of our agent's behavior. What we're going to do is compute the difference between the old Q value and the new Q value. So we're going to say the difference here is going to be Q new of SA minus Q previously that we had of SA, where this is going to be our new Q value is going to be 250. So we have 250, where action equals U and our state equals S. And what was our old value of QSU? Well, it was 280 over here. So minus 280. So this is going to end up in a difference of minus 30. Now, how does the update of each of these weights work? Well, we're going to take a particular weight, for example, WP, and we're going to say that WP equals the old value of WP plus our learning rate alpha times the difference in our Q values times the feature FP at state S after taking the action up. And so the old value of WP was equal to 100. Our alpha equals to 0.5, and our difference equals minus 30. And then what is the feature value of FP at state U? FP at state U is equal to 3. And so this ultimately will equal to a new weight for the feature FP of 55. What about WG? It's going to be the same process. It's going to be WG plus our learning rate alpha times the difference times now our feature G of SU. What was our old weight? It was minus 10 plus 0.5 times minus 30, which is our difference between the old Q value and our new Q value. And then what is the feature value of state S action U for FG? It's going to be equal to 2. So times 2. And if we multiply and add this all together, we get minus 40. And so you can see how after applying this weight update, the weight on feature G has gone from minus 10 to minus 40, and the weight on P has gone from 100 to 55. And so this shifting is going to start pushing the approximate representation of our Q values to be more and more aligned with the true Q values that we're trying to actually learn. And this is all by simply updating these weights, WG and WP, based on our feature values that we've encoded right here. All right, thanks everyone. I hope you have a nice rest of the day.